Hi, I'm Professor Goins. In this video, I'm going to show you how to find the tangent line to a space curve. So what I have is this purple graph. So this is a space curve. The function name is r of t. And what I want to find is the equation of the tangent line corresponding to a point on the graph labeled a t equal to c. So remember that the coordinates here would be x evaluated at c, y of c, z of c. So again, the coordinates of that would be x of c, y of c, and then z of c. So I'll just refer to it as the point corresponding to t equals c. All right, well, I have the graph and I know c, so therefore I can compute r of c, so just plug c into this function. And that would give me the vector starting at the origin and terminating at that point there on the graph. And this red dotted line is the equation I'm trying to come up with. All right, so what I want to do is I want to figure out for an arbitrary t, how can I get the vector that would go from the origin to this point right here? And the way I'm going to do that is using a derivative and then also using some vector arithmetic. Okay. Recall that when you take the derivative of a space curve and you, at any point on the curve, if I were to evaluate it, that the derivative evaluated at that point is tangent to the curve. So let's say, for example, I was going to compute the derivative at this point right here. And let's say this purple marker is the derivative evaluated at that point, then I know that it's going to be tangent to the curve. Well, the vector is tangent to the curve and this line is tangent to the curve, then that must mean that the derivative would be a vector along this line. And so let's call this, actually I'm going to do that in a different color. I'm going to do that in black so it distinguishes from the original curve. So let's see if I do that in black. That black vector right there would be the derivative of r evaluated at t is equal to c. So it's tangent to the curve at that point. Well, what I want to do is I want to figure out how can I get a vector that starts at the origin and terminates at this point. So that means I want to come up with the following vector. Okay, so you can see that if I were to add these two vectors right now, if I just take this blue vector and the black vector and I add them together, I would get the vector that goes from here to here. So I'd get this vector right here. If I want to get the green vector, then I have to stretch the black vector a little bit farther. So what I'm going to do is I'm going to multiply this black vector by a constant that will stretch it so that the tip of the vector lands at this point right here. And let's see, what colors do I have? Let's use red. All right, so what I'll do, and I'm going to try to screw my grip here by going over the black, but that would be this vector right here. So that'd be this red vector, which would be, the red vector would be a constant t times the derivative of r, and I know this is small, I hope you can see it, but I'll write it again below. So this red vector, I'm going to take this and just multiply it by a constant. Okay, so therefore, in order to get the green vector, I add the blue vector and that red vector, just using vector arithmetic. So that's the equation of the tangent line, because the value of t can just range over all real numbers, and any real number I plug in here will just generate all the points on that curve. So the equation of the tangent line, I'll use the following notation. I'll use L for line. I'll use a subscript C to just remind us that it's related to this value right here, and then of t. Since it's going to be a vector function, I'll put an arrow on top. So that right there will be my notation for the equation of the tangent line to the curve at the point C. And the formula for that, again, I evaluate R of C, and then plus T times the quantity dr dt evaluated at T is equal to C. And this is my formula for the tangent line. So let's do an example. So find the tangent line to the graph of R of t is equal to t cubed plus 1, t squared, and negative 4t plus 7 at the point where t is equal to 1. So we can see from our formula over here, the two things we're going to have to do is evaluate the original space curve at that point t equal to 1, compute the compute and then evaluate the derivative, and then just put them together. So solution. R of 1, so I plug 1 in for t, so that would be 1 cubed plus 1, which is 2. 1 squared would be 1. Negative 4 plus 7 would be 3. So this initial blue vector over here in our diagram would be 2, 1, 3. So that would be this vector right here that starts at the origin and terminates at the point of tangency. Then dr dt. So remember, to differentiate a vector function, I differentiate each component. So that'd be 3t squared, 2t, and negative 4. Next thing, I have to evaluate the derivative at the specific t value. So dr dt evaluated when t is 1. So that would be 3 times 1 squared, which is 3. 2 times 1, which is 2. And negative 4. That vector right there, that 3, 2, negative 4, just to match it up with our diagram, would be this black vector. So it's the derivative evaluated at that t value, which would be the vector that's along the tangent line, so it's tangent to the space curve. And then when we put it down here, we just put this scalar multiple next to it, or this variable that's going to provide scalar multiples of it. So then finally, I just have to add this vector here, and then t times this vector to get my tangent line. So final answer for this example would be L1 of t would be 213 plus t times the vector 3, 2, negative 4. And we could leave it like that, or we could combine it using vector arithmetic to give me 2 plus 3t, 1 plus 2t, and then 3 minus 4t, so 3 minus 4t. And just like we saw in one of our other videos when we did equations of lines, that has the same form. It's a constant plus a constant times t in each component.